All right, well, what a weekend, huh? Some of you were in line Friday night, and the testing center had a slowdown in their systems that prevented people from scanning in to take a test, also prevented bubble sheets from being scanned immediately. That was entirely beyond their control. There's a critical BYU system went down. And so what I did is I extended the deadline on the exam for those students that were still in line at the time the testing center closed. I apologize for all the stress, and if there's anything you need to talk about, any concerns you have, feel free to email me or stop by. There are a few students who haven't yet taken the exam, so I can't answer specific questions about specific exam problems, at least not in public yet. If you want to come talk to me in my office, totally willing to. I have office hours today right after, from 10 to noon, and feel free to email as well. Let's see, so interpreting your score. The average score on the exam, the mean, was 70%. That's lower than the previous exams. That's not unexpected because the material has gotten harder. The median 50th percentile score was about 72, so pretty close to the mean. Interpreting your score is when the mean or median is in the low 70s, interpreting your score literally in terms of the cutoffs that are listed in the syllabus is not a great thing, because the average score in the class ends up being in the low B range, B to B minus. So if you finished in the 70s, your score, if you finished at 70 to 72, your score isn't a C minus, even kind of. Your score is in the B minus to B range, okay? If your score is higher than the median, then the higher it is, the more likely it is that you're in the A range. If your score is below the median, say if the mean is around 70, the median's around 72, scores in the 60s would be in the C range in some kind. So some of you have emailed me telling me I totally failed the exam, and you did not. Likely, if you're finishing in the 60s somewhere, that's not close to failure. So I only assign letter grades at the end of the semester. I use the cutoffs in the syllabus as a starting point, but with the guideline from the department that the average score in the class historically tends to be in the B to B minus range, I adjust the cutoffs accordingly. The cutoffs between C minus and D tend to be in the low 60s. The cutoffs between B minus and C plus tend to be pretty close to 80. Of course, there's some variation. You got the first two exams where the averages were in the 80s. You got this exam where the average was in the 70s. We got a final coming up, and that final can replace your lowest midterm score. So there's just a lot in flux at this point. But if you can calibrate sort of how well you think you did on the exam based on where that mean or median score is, I think that'll be helpful to you. Any questions you guys want to ask? Yeah.
So does that mean that the class is kind of curved at the end?
Does that mean the class is kind of curved at the end? I think so, but why don't you tell me what you mean by curve?
Just like if I'm understanding correctly from what you're saying, like if we're above the average, does that mean we're more likely to have an A? If we're about at the average, does it mean B? It's like depending regardless of.
In the sense that, so I start with yes, there is a curve, by which I mean I adjust the cutoffs lower as justified by the class average. Now, I can't say what will happen this semester. I can say what generally happens. Often the cutoffs between, say, A minus and A, pretty close to 93, maybe 1, maybe 2 percentage points lower. Cutoffs between A minus and B plus, pretty close to 90, maybe 1 or 2 percentage points lower. That is, in the upper half of the class, the cutoffs stay pretty close to where they generally are in the syllabus. In the B- to C minus range, the cutoffs are quite a bit lower. Yeah. Yes. Other questions? Okay, well, if you think of anything. All right, let's finish talking about, well, okay, here's a common question. I've been working hard, I've been studying hard, and I'm still not seeing results. What do I do? And the answer to that is you and I need to have a conversation about what you're doing to study. Because if you're putting in the time and not seeing the results, then it's not an issue of time, but it may be an issue of what you're doing with that time. So I do have some suggestions. Feel free to come talk to me about it. The key is getting practice and understanding ahead of time what you're likely to make mistakes on and preparing for that. So that's hard. It's a different way of studying than many of you have done before, and I can provide some suggestions that generally do lead to improvement. And it's not too late, because with the final coming up, the final is worth almost twice, not quite, but almost twice what a midterm exam is worth, and the percentage score on the final can replace your lowest midterm score. So there's still a chance to improve pretty dramatically. All right, well, let's talk about radicals. So we ended last time, make sure we're capturing audio. Yes, okay. We ended last time talking about the regioselectivity of radical addition to alkanes. That is, we said that when you use bromine and react bromine under radical initiation conditions with an alkane, there's potentially two different radical intermediates that you get. Recall that the radical reaction involves, first, radical initiation, which is where we shine UV light and we break the bond between two bromines in a homolytic fashion to get two bromine radicals. That's our initiation step. Recall that our first propagation step is that the bromine radical abstracts a hydrogen atom from the alkane, and we said that there are two possible radical intermediates. One where we abstract the secondary hydrogen to get a secondary radical, and the other shown here where we abstract the primary hydrogen to get a primary radical. And we've said before that the more substituted radical is more stable, and so for bromine, that's our preferred intermediate. Then in a second propagation step, we generate the product as that carbon-centered radical now reacts with bromine to give you the bromine addition product and another bromine radical. And so we cycle through these two propagation steps indefinitely, and the preferred product is the one where the bromine ends up on the more substituted carbon, because you go through the more substituted radical, which is more stable. Okay, questions about that? All right, let's see how well you're doing. Let's imagine this starting material, radical bromination conditions. What's the product? This one's even more confusing because you have several different groups of CH bonds. In fact, I'm counting 5 different CH bonds that could potentially be abstracted. Where's the bromine going to end up? Green carbon, more substituted one that passes through the more substituted radical, which is more stable. Okay, and notice how this enables synthesis now. I think I've maybe mentioned this before, but you've had to do synthesis reactions where you generate something like this as a alkyne product, and maybe there were some other things you did to the alkyne product later on. But I've previously asked you to start with, say, an alcohol, and you can get the alcohol from an alkyl halide. But now you know how to get the alkyl halide from an alkane. So now it's possible to start a synthesis at an even simpler, more elementary step. Yeah?
This might be a colossally stupid question, but why are there only 5 CH bonds that we're looking at? What's with the others?
I meant 5 different kinds of CHs. So
Okay.
there are 3 here, 1 here, 2 here, 2 here, and 2 here. I was just saying different kinds of identical hydrogens. Yep,
Oh, gotcha.
yep, you bet. Others? Okay, so it turns out that you can do radical chlorination as well, but the chlorination reaction is not that selective. Bromination is selective. Chlorination isn't. So if we do this same reaction with chlorine, unfortunately, we're going to get all of the possible monochlorinated regioisomers. So here's in blue the one where chlorine goes on the methyl group. In green is where the chlorine goes on the tertiary carbon. And then the remaining ones are where chlorine goes on each of the secondary carbons. And you'll notice that in places where the chlorine is at a stereocenter, you'll notice that I'm choosing to draw just straight lines instead of dashes and wedges. And that is because the radical, the carbon-centered radical, remember, is sp2 hybridized. And the SOMO, the place where the single electron is in a p orbital. And that means that the radical addition step can happen from above or below. So you expect radical addition steps to give you a mixture of stereochemical configurations if you make a stereocenter. That's why I've chosen to use straight lines instead of dashes or wedges. And notice it gets kind of confusing. You start here, and this carbon, the tertiary carbon, is not a stereocenter. But all of a sudden, you put a chloro at this secondary carbon. Now you got 2 stereocenters. These 2 lines, straight lines, communicate all possible configurations at both stereocenters. So you expect dashes and wedges in all possible combinations. Same thing here, same thing there. Okay? All right. So one question we could ask is, why is chlorination not selective, but bromination is? And this has to do with the reactivity of chlorine versus bromine. So let's contrast this. On the left, we'll put bromine, and on the right, we'll put chlorine. It turns out that the bromine-bromine bond is weaker than the chlorine-chlorine bond. And remember, a stronger bond means more stable. the weaker bond in bromine-bromine means that relative to Br2, the bromine radical itself is more stable relative to Br2, whereas Cl radical is less stable relative to Cl2. Okay? So that conclusion may not look completely obvious. Let's just say that because the bromine-bromine bond is weaker, you don't have to go up as high in energy to break it, and that makes the bromine radical not that unstable. The chlorine-chlorine bond is stronger, so you have to go higher in energy to break it, meaning that the Cl radical is less stable. Okay? So that's the first observation, that the Br radical is less reactive than the chlorine radical. And remember, more reactive means higher in energy. Less reactive means lower in energy. So you'd expect Br minus to, or Br radical to be lower in energy than Cl radical. All right, let's talk about how that might influence the step of the reaction where, and we'll just, as our starting material, we'll choose this simple propane that has a primary carbon and a secondary carbon. You've got two possible reactions for both of them. One is that, one is that bromine removes the secondary hydrogen atom to get the secondary carbon-centered radical. There's two hydrogens on that carbon. We're just showing one of them being removed. I don't like that. Let's try this. And the alternative is for bromine to remove a primary hydrogen. To get the primary carbon-centered radical. Here. And of course, we could do the same for chlorine, the two mechanistic possibilities for chlorine. So I'm just going to copy and paste that. And I'm going to replace the bromines with chlorines. So that's the step that generates the radical. Okay? Now let's do an energy diagram for bromine for this first step. Before the reaction, the starting materials, you have the alkane and you have Br2. No, you have Br radical. Now, we're not doing the radical initiation step. We're focusing on the step that generates the carbon-centered radical. The starting materials for these pathways, getting to the secondary radical versus the primary radical, the starting materials are exactly the same. So we're going to begin here. However, we end up, and I need to go down, a little bit lower in energy. We end up at either a secondary radical or a primary radical. And it turns out that relative to Br radical, the carbon-centered radicals are higher in energy. So we're going to put the secondary carbon-centered radical here. And we're going to put the primary carbon-centered radical here. And because this first step, the starting material going to the carbon-centered radical, this first step is endothermic, it's uphill. And therefore, the transition state leading to the primary radical is higher in energy than the transition state that leads to the secondary radical. So it will turn out that the secondary radical forms fastest because of the Hammond postulate. The transition state that leads to that secondary radical is more stable than the transition state that leads to the primary radical. Follow the reasoning. If bromine radical is fairly stable, the hydrogen abstraction step is uphill in energy. You're going uphill to the carbon-centered radical. Because you're going uphill, the transition state that leads to that carbon-centered radical must be somewhat radical-like, and therefore the transition state on the blue path is lower in energy than the transition state in the red path. Kind of convoluted, but it's another example of what we learned about in the SN1 reaction called the Hammond postulate. That is, transition states resemble the intermediate or starting material that they are closest to in energy. Okay, questions about that? So let's see how the situation changes with chlorine. It turns out that the primary and secondary radical products secondary radical intermediates are, of course, same in energy as with bromination. However, for chlorination, the starting materials are up here because chlorine is less stable than chlorine radical is less stable than carbon radical. So therefore, the transition state that leads to the secondary radical and the transition state that leads to the primary radical are pretty close in energy. Meaning they're similar in energy for the, oops, I got it wrong, secondary versus primary radicals. And what this means is that they form at similar rates. So there's no selectivity. Again, this is an application of the Hammond postulate. The transition state is closer in energy to a chlorine-centered radical than to carbon-centered radicals, and therefore radical stability matters much less for chlorine than it does for bromine. Okay? This is an example of it's a useful way sometimes, it depends on the mechanism, but it's a useful way of thinking about reactivity and selectivity. Sometimes we find in organic chemistry that more reactive starting materials are less regioselective. And this is a case where that's true, and it's true because the more reactive starting material has a transition state that looks more like starting material than it looks like radical products. And so, because it looks more like a chlorine radical than a carbon-centered radical, there's no difference in energy for those transition states, and there's no selectivity for primary versus secondary. All right, anything you want to ask about that? Make it stop, right? Well, fortunately, you only have like 20 minutes and you're done for like a week, so yay. Okay. What I want to do next is sort of, we could talk about fire, or we could talk about plastic, or we could talk about rancid oil and allyl radicals? Fire? Okay, yeah. So I had it's been a few years now, I had a student come to my office, and I don't think they were actually enrolled as a student in my class, but they're like, dude, I heard you're an organic chemist. And I'm like, yeah. So I want to explode a turkey at Thanksgiving. I'd like to explode a turkey, and I'm hoping you can help me out with the explosives. And I was like, where do I even begin? First off, there's no way in heaven or hell that I'm going to tell you how to create a bomb to blow up a turkey, okay? It's just not happening. Second, please do not go do it on your own, because the frozen turkey, it's going to create shards and bones that are going to go out in all directions. And he informed me that in the state of Texas, it was quite common to fill up a turkey with something flammable and shoot it, and see what happened. So I never saw the student again, but I know that my conscience is clean because I did not tell him how to blow up a turkey. I'm not sure I know how to blow up a turkey. All of you going home, please do not blow up a turkey. Don't do stupid things, all right? I'm recording that. I'm going to put this on YouTube, so hopefully for posterity, there's this record out there that I said on this day, please do not blow up a turkey. All right. But you do want to know about fire, huh? Okay. Let's talk combustion, because combustion is the radical reaction with which you probably have the most day-to-day experience. If you've lit a candle or grilled or blown up a turkey, then you have seen some combustion. So here's a simple combustion reaction. Methane plus 2 molecules of oxygen goes to CO2 and 2 molecules of water. Looks really simple, and you can calculate the energy released upon this reaction. Things like release of energy are what we call state functions in chemistry, and state functions don't depend on how the reaction happens. They just depend on the starting point and the ending point. It turns out there's probably hundreds of sub-reactions that are going on here. Maybe not hundreds for methane, but people study combustion and they study all the reactions that can happen, and it's not simple. So let me show you a few things that can help you understand what's going on with combustion. First, you've drawn the Lewis structure of oxygen before, and you've probably drawn it like this. However, it turns out that oxygen is perhaps better thought of as, and this is because of MO theory, in oxygen, if you fill up the orbitals, there are 2 pi bonds in oxygen, but the last energy orbital, well, for the HOMO, instead of having 1 highest occupied molecular orbital, you actually have 2 equal in energy highest occupied molecular orbitals, so the final pair of electrons goes one in one and the other in the other. So oxygen is actually like a diradical. And that means oxygen's pretty reactive. We think of oxygen as life, right? You gotta breathe to live, and oxygen gives us life, and that's true. But oxygen's also highly reactive, and biology has evolved to deal with this using things called antioxidants. But if we were to draw a Lewis structure that sort of better maybe represented oxygen's structure, it would be difficult to do because we're missing a pi bond, but doing something like that is not that bad. There are 2 different radical states of oxygen. There's the singlet state and the triplet state. You don't need to worry about what this means. I'm just drawing the 2 highest occupied molecular orbitals. In the singlet state, the electrons in either of those two orbitals are opposite in spin. And interestingly, this state is less stable. It's higher in energy, and it's more reactive. So you may have heard of people talking about singlet oxygen, and singlet oxygen is more reactive. This is triplet oxygen. Why it's called singlet and triplet doesn't really matter for this class. If you want to know more, you should take PChem. But the triplet version of oxygen, where the spins are parallel, is more stable. There are some, so when you have singlet oxygen, it's reactive enough to start doing radical chemistry with hydrocarbons. And this is why you need heat to start a fire. You need to have enough energy to excite oxygen to the singlet state. So here are some example reactions that occur in fire. Okay, so here is, let's just tell you that this is singlet oxygen. And we'll draw it as we've done above. And then here's your hydrocarbon. So, hydrogen atom abstraction takes singlet oxygen and converts it into this, which is called the peroxy radical, and then this, which is methyl radical, a carbon-centered radical. All right? Now, there's a lot of different things that can happen to that methyl carbon-centered radical. One of them is a radical recombination step where the methyl radical meets the peroxy radical, and you create a new carbon-oxygen bond. And if you're looking at where we need to end up with CO2, each carbon needs 4 bonds with oxygen, so you can imagine this process has to happen again and again and again. Now, there are a lot more steps. I'm looking at probably 6 or 7 more steps before you get CO2. If you want to see them all, we can do them here, but perhaps you don't. Perhaps this is enough of an example of what's going on in combustion. Do you want to see more, or are you okay? You're good? Yeah, that's the question. Is it going to be on the test? Well, if I talk about it, sure. So I should stop? Is that what you're saying?
Yeah, we're good right here.
We're good right about there, okay. If you want to know where the light in fire comes from, there's a couple of things that are possibly worth noting. So along the way, one of the radicals that you can make as this process happens is called methylidine radical. It's weird, and I wouldn't expect you to be able to draw how this forms, but this is one of the things that can form. And in a flame, if the methylidine radical gets excited and then relaxes, it shoots off a photon of light, and that light is blue. So if you've ever grilled on a propane-powered grill or oven and you see the light is blue, one of the things you're seeing is an electronic transition as methylidine radical gets excited and then relaxes. Also, a transition that occurs in that region of the spectrum is you form C2. This is weird. You didn't know that that could exist, and it doesn't generally, but it does in flames. And this also, both of them, C2 is not called methylidine radical, but both of them do excitation and then relax. And as they're relaxing, they release a photon of blue light. You've noticed that in some fire, you see not only blue, but you see yellow. And it turns out that the yellow color you see is just black body radiation of soot particles. So depending on the amount of oxygen you have present, some of these radicals can recombine to form various carbon structures. This is soot and ash. And these particles get hot, and when particles get hot, they start to radiate. If you have a regular stove where you turn up the temperature and you see something that's glowing red, that's black body radiation. So the yellow light you're seeing is just particles being heated to really high temperatures and glowing as a result. Okay, that's fire. Shall we talk rancid oil or plastics? Plastics, all right, yeah, we've already talked rancid oil, so you have an idea of that. Yeah, so plastic polymerization is, in many cases, not all cases, but in many cases, it's a radical process. So, and we'll talk about this again at the end of 352. But of all the things that you interact with in your daily life, this is possibly, aside from taking medications, this is possibly the major touch point you have with organic chemistry in your daily life. So radical polymerization, let's show you how this can happen. For a polymer, you need a subunit that's called a monomer. And you're going to pack together multiple of these monomers into one molecule. So here is an example of a monomer. It's called vinyl chloride because you've got a chloro attached to the vinyl carbon. And in radical polymerization, you have some starting radical. You need an initiator. So we'll just call this your radical initiator, and that can be a lot of different things. It turns out that that radical initiator only forms a very small portion of the polymer, and so often it actually doesn't matter what that radical initiator is, because most of your polymer is going to come from your monomer. So this is a new reaction with radical chemistry, one that you haven't seen before. This is radical addition to a pi bond. You can think of this in two different ways. You can think of the radical as attacking the pi star, or you can think of the pi bond as a nucleophile attacking the radical, and either way is fine. It turns out the radical will preferentially form a bond with the less substituted carbon, so that the more substituted carbon can get the radical where it's more stable. So here is your new bond to the less substituted carbon of the alkene, and then here is your radical, and through resonance with lone pairs on the chlorine, that radical is resonance stabilized, okay? Well, now we've got a new carbon-centered radical, and so we can bring in a new monomer. We can do the same reaction again, and now our monomer is extended, our polymer rather, is extended by one monomer unit. And so we might continue indefinitely until we run out of monomer. Each time we do a radical addition reaction, we're adding one more monomer to the growing chain. Sure. And at this point, I'm just going to do etc. Because at the end, you end up with a huge polymer that extends infinitely, well, not infinitely, but extends like crazy in multiple directions. And you have each of these 2 carbon units linked together. I'm going to use squiggly lines to indicate that the polymer goes on in both of those directions, and I don't like that bond there, so there we go. This is called polyvinyl chloride, or PVC. And if you look at the bottom of or the back or whatever of a container, if it has the recycling symbol 3 on it, that's PVC. So yeah, go ahead.
Question, you said that there was resonance stabilization with whether that was found on the monomer.
Yeah.
If that results in any reactivity of polymerization on the chlorine rather
Great question. Does it result in any polymerization on the chlorine? Not that I know of, because that would require chlorine to have 2 bonds to it, and it would have a positive formal charge, so it's just more stable to polymerize on the carbon. So anybody out there ever worked on a sprinkling system before? You worked on PVC pipe? Yeah. Okay, so you've had that experience with PVC pipe, fittings, flooring. Different plastics have different properties, and this can be kind of a challenge. PVC tends to be a little bit brittle and to not have a huge amount of ability to expand with temperature. I know this because of my own sad experience, and it's been more than 10 years. But when we moved into our house in 2011, the sprinklers in the front yard were installed, and I had to do the sprinklers for the backyard, which was fine. It was actually not fine. It was a miserable summer. But anyway, they told us that you needed to blow out your sprinklers before the winter, because if you left water in the pipes and they froze, the pipes would break. And so I figured, okay, well, it probably can't be that bad. I did blow out the sprinklers for the first year, but after that it was like, So I pulled off the backflow preventer, which prevents backflow, surprisingly, of water into the house. And I thought, you know, if as long as I pulled that off, there's a place that's open to the air that water can expand. That was a stupid thing because it really wasn't that way. In any case, the next spring when I go to start up the system, do you know in the book of Ezekiel where it talks about water pouring forth from underneath the steps of the temple and then healing the world? Well, I didn't heal the world that day, but I did turn on the sprinklers, and a portion of my lawn literally lifted up as water was pouring out from under it. And it turns out that a big long stretch of PVC pipe had literally shredded, like cracks, spiraling cracks in all directions. I had to dig up my lawn and pull that out of there. And I haven't made that mistake more than 3 or 4 times since that point. But anyway, some plastics don't expand very well and then get cracked. And so PVC is one of them. There are molecules that you can put in plastics that help allow the plastic to expand. These are called plasticizers, and I don't have any good examples of them for you right now. So let's do a couple of other radical polymers so that you can at least see their structures. A lot of these are just named according to their monomers. So if you do radical polymerization with say ethylene, then the resulting polymer is called polyethylene. And so I'm just going to copy and paste the structure of polyethylene, but I'm going to erase, oops, that didn't actually save me any time, did it? All right, well, for polyethylene, there is no sort of side chain hanging off group. Polyethylene is just this long hydrocarbon chain because instead of having chloro at one of the carbons, you just have hydrogen, right? And what does the presence of polyethylene do? What does the presence of the chloro do in PVC versus polyethylene? It turns out there are multiple kinds of polyethylene. What I've drawn for you here is called high-density polyethylene, and if you see this on a recycling container, a recyclable label on your plastic, it'll say 2. High-density polyethylene is fairly rigid and robust. There is something called low-density polyethylene, and this is way more malleable. So water bottles that are sort of squishy are often made out of low-density polyethylene. And you can see, if you've seen a PVC pipe versus polyethylene, polyethylene can be transparent. You can sort of see through it. PVC, generally not. This is an example of a principle we like to talk about in OChem called structure and function relationships, where the structure of a polymer determines its function. I can illustrate that with by contrasting the structure of high-density polyethylene with low-density polyethylene. So it's a difference in how the polymerization process occurs. We won't talk about it now, but we will perhaps in 352. It turns out that in low-density polyethylene, you can get branching of the chain. And why and how this happens is not immediately evident, and that's fine, we'll talk about it later. But it turns out that branching does, for polyethylene, what cis double bonds do for fats and oils, right? You remember learning that the cis double bond in a triglyceride prevents the nonpolar tails from packing against each other very tightly. That decreases the strength of the van der Waals interactions and makes something a liquid when it has a cis double bond in the backbone versus a solid when it doesn't. In high-density polyethylene, there's no branching, and so those polymer chains can get very close to each other, and the van der Waals interactions are quite strong. In low-density polyethylene, they can't. Because of the branching, they're forced to stay apart because of those covalent bonds. That makes low-density polyethylene much more malleable. So you'll see, like I said, low-density polyethylene in some plastic bags and in squishy water bottles. You'll see high-density polyethylene in like laundry detergent bottles. All right, well, have a good Thanksgiving. I will see you in a week.